Right now, you are being pulled apart. Not violently, not yet. Somewhere in the space between the atoms of your body, a force is stretching everything by an amount so small it will never register on any scale you own. You will never feel it. Not today, not this year, not in your lifetime, not in the lifetime of your species. But it never stops. And if that force keeps behaving the way it has for the last several billion years, one day it will tear apart entire galaxies, then stars, then planets, then you, faster than light itself can travel. That last part sounds impossible. Nothing outraces light. Except space. Space doesn't play by that rule. Scientists have a name for the moment when that stretching finally wins against everything holding the universe together. They call it the Big Rip. And to understand how something that sounds like science fiction became a serious scientific hypothesis, you have to go back to the moment humans first realized the universe was moving at all. In the 1920s, an astronomer named Edwin Hubble was studying faint smudges of light through the telescope at Mount Wilson Observatory in California. Those smudges turned out to be entire galaxies, far beyond the edge of the Milky Way. Hubble noticed something strange about their light. It was redshifted, stretched toward longer, redder wavelengths, the same way a siren's pitch drops as it speeds away from you. Stretched light meant only one thing. Those galaxies were moving away, almost all of them, in every direction. Hubble had just discovered that the universe itself is expanding, carrying galaxies apart the way dots on an inflating balloon drift from one another as the balloon fills with air. Not moving through space exactly, but riding along as space itself grows between them. For decades afterward, scientists assumed that expansion had to be slowing down. Gravity, after all, pulls things together. Every galaxy in the universe is tugging on every other galaxy, so logically that mutual pull should be putting the brakes on the whole expanding system, the way a ball thrown into the air slows as gravity fights its climb. In 1998, two independent teams of astronomers set out to measure exactly how much the expansion had slowed. One team was led by Saul Perlmutter. The other included Brian Schmidt and Adam Rees. They used a special class of dying stars called Type 1a supernovae, stellar explosions so consistent in brightness that astronomers use them as cosmic measuring sticks. By comparing how bright one of these explosions appears from Earth to how bright it should be at a known distance, astronomers can calculate exactly how far away it sits, and by measuring how stretched its light has become, how fast it is receding. Both teams expected to confirm a slowing expansion. Instead, they found the opposite. The expansion of the universe was speeding up. That result was so unexpected that both teams initially assumed they had made an error. They checked their data again. They checked it again after that. They hadn't made a mistake. The discovery was so solid it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Something was fighting against gravity on a cosmic scale and winning. Scientists gave that mysterious something a name before they even understood what it actually was. They called it dark energy. Dark energy isn't a typo for dark matter, and it isn't the same thing. Dark matter clumps around galaxies and adds extra gravity, holding them together. Dark energy does the opposite. It fills empty space itself and pushes everything apart. According to precision measurements from the European Space Agency's Planck satellite, which spent years mapping the faint afterglow of the Big Bang across the entire sky, dark energy makes up roughly 68% of everything in the universe. Not 68% of the matter you can touch or see, 68% of everything that exists, including the very fabric of space you are sitting inside right now. So what happens if that pushing force never lets up? That question comes down to a single number physicists call the equation of state, usually written as the letter W. Think of W as a description of how dark energy's pressure behaves as space stretches. If W equals exactly -1, dark energy stays at a constant density forever, no matter how much space expands around it. That scenario leads to a slow, cold fade, called the Big Freeze. Stars burning out one by one, galaxies drifting into darkness and silence until the last ember in the universe goes quiet, trillions of years from now. But if W drops even slightly below -1, into a regime physicists nickname phantom energy, everything changes. Dark energy doesn't just stay constant, it grows stronger as space gets bigger. And the force that keeps intensifying as it works doesn't fade towards some gentle equilibrium. It runs away, faster and faster, with nothing in the laws of physics able to slow it back down. In 2003, physicist Robert Caldwell modeled exactly what that runaway scenario would look like, mathematically, all the way to its logical end. He gave the resulting Doomsday its lasting name, the Big Rip. So picture it, not as an abstraction, but as an actual timeline counting down. Tens of billions of years from now, galaxy clusters are the first to go, since they are only loosely bound by gravity across vast distances. The stretching finally outpaces the pull holding them together, and clusters that have traveled alongside each other for billions of years drift apart for good, each galaxy sliding into an isolation of its own. 60 million years before the end, individual galaxies unravel. The Milky Way, long since merged into Andromeda into a single galaxy, comes apart star by star, each one flung into an emptier and emptier sky, until any sky left behind would show nothing at all. 3 months before the end, planets unbind. Planets no longer held in orbit by gravity too weak to compete with the stretching of space, drift away from whatever star once warmed them, carrying their oceans and their atmospheres out into a widening dark. 30 minutes before the end, planets themselves are torn apart, their own gravity no longer strong enough to hold their crust to their core. And in the final fraction of a second, the stretching reaches down into matter itself. Molecules separate, atoms separate. Then the strongest force known to physics, the one that binds particles inside the nucleus of every atom, finally loses its grip. Space itself tears every remaining particle away from every other particle, at a rate faster than light could ever cross the gap between them. That's the Big Rip. A universe that doesn't fade quietly into darkness, but unravels, thread by thread, faster and faster, until there is no thread left to pull. Here's the twist, though. Nobody actually knows if this is how your universe ends. Every measurement so far puts the value of W extremely close to -1, but not quite precisely enough to rule either fate out. The difference between a slow, cold fade and a universe-shredding rip comes down to a sliver of a decimal point that current instruments cannot quite resolve. The single most consequential number in cosmology, the one that decides whether everything ends in ice or in violence, is currently a rounding error away from being known. That's not a failure of science. It's a live investigation, happening right now. The European Space Agency's Euclid Space Telescope, launched in 2023 and now orbiting a gravitationally stable point roughly 1.5 million kilometers from Earth, is spending years mapping the shapes and positions of billions of galaxies, specifically to pin that number down with far greater precision than any instrument before it. So while you go about your day, unaware, unstretched, feeling nothing at all, a spacecraft far past the moon is quietly gathering the evidence that will eventually tell your species which ending is real. No urgency to it, no countdown clock ticking anywhere you can see, just data arriving one galaxy at a time. Isn't that strange to sit with? For 13.8 billion years, the universe expanded without anyone around to notice, let alone ask how it would end. Trillions of stars lived and died with no witness at all, and now, for one brief, improbable moment in cosmic time, a version of the universe complex enough to build telescopes, launch them 1 million miles from home, and ask the question out loud exists. That's you. That's this exact moment, and no other. Right now, you are still being pulled apart. So is every atom in every star, in every galaxy across the entire observable universe. The only difference between you and the ending of everything is time, and one decimal point nobody has measured yet. You will finish this sentence, stand up and go on with your day, unaware and unharmed, but the stretching will still be there tomorrow, and the day after that, and for the first time since the Big Rip was ever calculated, somebody is finally watching the numbers come in.